everyone, welcome back to Learn Computing with Daniel Bullen. Today we're going to do something really exciting as if we've got something really exciting lined up for you. We're diving into the world of floating point representation in computers, and what better way to do that than creating a Python program together. So buckle up, hit that like button and that subscribe button and the notifications bell, and let's get started. So let's see the program that we want to get to work first. So I'm going to run it, and let's say I want to type in a number like 6.75 in decimal, and I want to find out the binary. That is our binary representation using the 8-bit mantissa and the 4-bit exponent. Let's say I want to go back to decimal. So I'm just going to convert any old binary numbers like these. So there's my 8-bit mantissa. I'm going to do a 4-bit exponent. Yep. So that is as accurate as a representation as I can get it in Python. So to do this, it would be worth us going through how to actually do floating point binary, converting from decimal to binary using the 8-bit mantis and the 4-bit exponent, and the other way around. So floating point binary is a method of representing a fractional value, when the idea of standard index form is used to enable fractional values to be stored more effectively than with fixed point. And representing numbers in floating point will allow a greater range of positive and negative numbers, including decimal numbers, to be stored in the same number of bits. And it's called floating point because the number of digits is fixed, but the decimal point floats around. So in place values, so if you've been to elementary school or primary school, you would have been taught place value, never ever 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 move a decimal point. Only the numbers from tenths, hundredths, units. So hundreds, tens, units, point, tenths, hundredths, thousandths. But the decimal point, never ever move it. Floating point, you can move a decimal point. And the nature of floating point, you can move the position of a decimal point wherever you like, to a position that makes best use of available memory and storage. And that allows more of the storage to be allocated to the integer part or the fractional part as you need to. Uses of floating point in computing are numerous, and it can be used whenever increased precision is needed, often in engineering and science applications. So say we want to calculate the size of the electrons. Use floating point to do that. And if you want to deal with large quantities for calculating distances between planets, floating point is used, and more precision is given over to the integer part. So when dealing with distances as large, 0.25 kilometers on the end, that's insignificant. You'll also use it in, say, I don't know, aircraft's decent angle is if it's slightly out, it's going to crash. So you would need an autopilot system to deal with such angles. Floating point, here we come. Floating point to the rescue. Let's say you want to run a physics laboratory and need to measure energy given off by colliding particles. These energies are very small, and so again, floating point to the rescue, because it's going to be useful. So in floating point, the binary can move left or right depending on the number that we need to represent. And it's made up of two parts, mantissa, exponent. And both parts will also use 2's complement rules to represent negative numbers. Advantages: floating point, greater range of numbers able to be represented. It's best choice if increased precision is desired, due to the ability to represent large or small numbers, but complete precision, still unlikely. It's also widely understood by other programmers and widely used. There are ISO and IEEE standards for floating point. Because it's a standardized data type, interoperability between applications should be improved. But the complex calculations, as the floating point number needs to be deciphered first, leading to slower processing times. Complete precision is unlikely, depending on the number that we want to represent. And you need more storage space compared to fixed point and integer forms. So let's have a look. So we can this can be imitated using binary floating point representation. So you get the mantissa, that's represented as a fixed point binary number. Could be sign of magnitude or 2's complement. Number of bits allocated to this determines the precision of the number. So how small a fraction can be stored and how accurate the number is. Exponent is represented as a separate binary number, either a sign of magnitude or 2's complement, or just a positive. Number of bits allocated to this determines the range of the number, the maximum and minimum numbers that can be represented in any given amount of memory. So, for example, let's convert the binary to decimal using floating point. So we've got the 8-bit mantissa and the 4-bit exponent. So the first 8 bits, that's the mantissa, last 4 bits, exponent. Right. Let's have this example out, shall we? First bit, work out the exponent. And the exponent is 3. How do we know that? If we write it in binary form, 0, 0, 1, 1, 2 plus 1, that's 3. Done. Worked out the exponent, no problem. Right. Then we calculate the mantissa. Binary point is placed after the most significant bit. Yep. And then what we do, so 0.5 plus 0.25, that's 0.75. Mantissa, done. And then we do the following. We multiply the mantissa by 2 to the power of wherever the exponent is. So in this case, the exponent is 3. So it's 0.75 times 2 to the power of 3, giving us 6.0. And that's our final answer. That's how you convert from binary to decimal, using floating point with the 8-bit mantissa and the 4-bit exponent. We want to convert from denary to binary using floating point, so we're essentially going back. 6.75, let's have a see how that works, shall we? So you got 4 plus 2, that's 6. 6 plus half, 6.5. 6.5 plus a quarter, 6.75. So we need to convert that back to binary using the 8-bit mantissa and the 4-bit exponent. So we also need to normalize the number, so it's moving a binary point to that. For a positive number, the number starts with 0, 1. It's a negative, it's going to be a 1. So let's have a look, shall we? 6.75. We can move the digits, or we can move a decimal point. We can move a decimal point 3 places to the left, or we can move all the ones 3 places to the right. I prefer to move them 3 places to the right. So therefore, either way, you're going to have 0.11011000. So it doesn't matter which way you do it, you can move a decimal point 3 places to the left, or the ones 3 places to the right. Doesn't matter which way, they're both going to be right. So we need to move an exponent to show us 3 places to the right. So that's our mantissa. And our exponent is 0011 because we converted 3 back into binary. So that is 6.75 using the 8-bit mantissa and the 4-bit exponent. And that is the working procedure complete. If you're doing A-level computer science, whether it be AQA, OCR, WJC, or Cambridge International, that is the type of question in which will come up every year. It's a question you've got to ask. So if you can get the procedural mastery of these, you're laughing. Without further ado, this is what we're going to need to do. So we need to do a subroutine such as def, decimal, to binary, floating point, and we're going to pass decimal number as the parameter. So now we need to do sign bit, because we need to sign it 0, which is going to be a positive, if decimal number is greater than or equal to 0, else we're just going to have a 1. And then what we're going to have in here, we're going to have, what I should have done here was 2. And then what we're going to have in here is decimal number equals abstract decimal number. So that is the first bit that we need. And then what we will need to do is we need to extract the exponent, the mantissa, and the exponent. So what we need to do that is we need to extract, so we declare the exponent variable to 0. While decimal number is less than 1, we're going to do decimal number times equals to 2, and then we're going to decrement the exponent using the minus equals. While decimal number is greater than or equal to 2, decimal number is going to be divide equal to, and I'm going to increment the exponent. And then the next stage is normalization. So the normalization bit, exactly the same. While decimal number is less than 1, we're going to do times equal to, decrement the exponent. While decimal number is above a 2, it's going to be divide equal to, and increment the exponent. And then what we'll need to do then is we will need to convert the binary number. So we need a complicated formula where we're going to have the mantissa equals format. So we're going to format that so it's decimal number times 256, which will give you 8 bits of 1s and 0s, which is 1 byte. Hence why we've got the colon and the 8. Okay? So exponent bits, so we're going to format it to exponent plus 7, which is going to be up to 4 bits. And then we're going to do a return statement returning the binary representation. So that is decimal to binary. We will, however, need to do it the other way around as well. So we need to do we need to do binary to decimal this time. And it's going to be much the same way. So we've got binary to decimal floating point, and we're going to pass binary representation as the parameter. So you've got the sign bit being a binary representation of 0, which is going to be a positive. Like we said, otherwise a 1 is going to be, if it's a 1, it's a negative. So we've got the exponent, 1 and 5, 2 minus 7. Then the mantissa, it's going to be the binary representation. And then what we will need now is to calculate the mantissa. So that's going to be 1 equals 1 plus whatever the sum int bit is, times 2 to the exponent of minus I minus 1. So the I bit's going to be the enumerate, which is the mantissa bits. And then the decimal number is going to output minus 1 to the exponent of the signed bit times the mantissa times 2 to the power of the exponent bits. So times 2, exponentation is like to the power of. And after that, we are just going to return decimal number. So those are our 2 basic subroutines. Now we can get to the big daddy, where we can actually do the typing where we actually convert it. So you've got your decimal input. So it's asking us to enter a decimal number. Then you've got the binary representation where we're going to call the subroutine decimal to binary floating point, using a decimal input as the parameter. And then the binary representation is essentially going to be binary representation. And then same story for the mantissa. When we want to convert binary to denary, we type in the 8-bit mantissa, type in the 4-bit exponent, and then we got binary to decimal floating point subroutine where we're call using the user binary representation as its parameter. And then we're going to print out the decimal representation to that. Okay? So let's have a look and see that actually working. So let's run it. So I'm going to type in 7.5 or 7.75. That's given us the 8-bit mantissa and the 4-bit exponent. Yes, it is rolled into 12, but it's 8 bits for the mantissa, 4 for the exponent. So let's say I decide to do 0100 1, 1, 1, 1. That's your 8-bit mantissa. Then the exponent, I'm going to do 1, 0, 0, 0. That's your 4-bit exponent. 7.75. Nice and easy there. So that is how we do floating point in Python using the 8-bit mantissa and the 4-bit exponent, converting from binary to denary. So it's a nice little quick tutorial, and it's a sort of question that comes up every year, whether you're doing the A-level computer science spec for WJC, OCR, AQA. It's the sort of question that comes up every year, a question that they got to ask, basically. So we've got all the exciting bits. So we've inputted our own decimal number to see what the Python script will do. And then we've got the fun part where we've reversed the process altogether, inputting the 8-bit mantissa and the 4-bit exponent, and we converted that back into a decimal number. So think of it as decoding a secret numerical message. So that is what we've covered, and there's quite a lot to cover there. Okay, so I would watch this video again and again, just so you know how the process works, especially if you want to make this in Python. So please be sure to hit that like, and please also remember to hit that subscribe button. And another way to subscribe is to just click on this link, which is below each video I place. And if you like my content and you want to find out more about what I do, I've also got an online course called Introduction to Computer Systems on the Udemy website. So you just need to click on it, and there we go. So this is my online course, Introduction to Computer Systems. So this is the landing page for that course. So in it, you will learn. So these are some of the things we'll learn, like explaining the role of the central processing unit, describe the components of the CPU, provide an introduction to assembly language, which is low-level programming, explain the factors that affect the performance of the central processing unit, and I've also put in another bit that I'm interested in, the physics of overclocking the CPU, which made me develop an interest in electronics and also physics. So there's a lot more to it than even we realized. So this is the course content. So you've got computer systems, so I'm introducing you to it. Then I'm going into the different forms of architecture and assembly language. Then I'm going into the factors that affect it and the physics of overclocking the CPU. And then I'm going into logic, so combinational logic systems, making the logic gates, sequential logic systems, semiconductors. Then I go into all things binary, where we introduce you to number systems, all the way down to doing binary and sound, images and text. And then finally we got input and output devices and the different forms of storage, so that's where memory will come in. And then my assessment is basically one big quiz of 30 questions. So you don't need any knowledge to do this course. All you need is a computer with stable internet connection. So that's all you really need there. And why you should do the course? Well, wherever I don't know, I'll go out and learn it. So the way my brain is wired is I'm on the autism spectrum. So it will be an asset in helping you get through the online courses that we provide. So we understand how to explain things in simple terms due to my teaching background. So you could think of us as a real-life version of, say, a Sheldon Cooper from Big Bang Theory, minus the rudeness, or a C-3PO, but without the glitches. So I'm on the autism spectrum, so we're on the autism spectrum and have a rough idea on how to talk to them and relate to them. And my teaching style is that style I've crafted, and one that works in a way that some people don't get if they only had tuition in the classroom or just want to study the subject a lot more. So this course provides you with the opportunity to go further than you would in the subject that you want to pursue. So those are some of the reasons why you should consider buying this online course, because once you buy it, it's yours for a lifetime. For some of my videos, I will go through programming tasks. So if you want to do these yourself, I have put a Replit link below on my programming videos. So you just click on REPL, and this is what you need if you haven't signed up at all. So you just click sign up. If you've got an account, you just click login, and once you've logged in or signed up, this is the page that will appear. So if I was to log in right now, this is the page. So this will appear. So that will be the page there. And in addition to all that, I am also a private tutor where I offer my private tutoring services specializing in ICT and computer science. And I look forward to you coming to me for lessons. Goodbye for now.